So hello guys, today I'm going to go through some of the calculation problems related to chemistry. So first, let's look at the calculation examples that I didn't go through in the lecture. So the question is, how many grams of CO2 are obtained by complete combustion of these grams of butane, which is C4H10? So here shows the linear thought, but I will go through it by myself. So first we need to calculate the chemical reaction. So for the butane C4H10, it will have the combustion with oxygen, and it will generate CO2 plus water. And then we can balance this equation. So this should be 2, this is 13, and this is 8, and this is 10. By having this equation, we know that the butane, the coefficient is 2, and the CO2 is 8. And then we want to know the amount of butane and then the amount of CO2. So we know that the molecular weight of butane, C4H10, it equals to 12 times 4 plus 10. So the molecular weight of butane is 58. Gram per mole. And then we can calculate the amount of butane, C4H10, and so it equals to, we can use this mass divided by the molecular weight. So the result is 0.152 mole. So this is 0.152, and then we want to know the amount of CO2. Then we can use the ratio relation of 2 over 0.152 equals to 8 over the amount of CO2. And we can solve this equation. So the amount of CO2 equals to 8 times this one and divided by this one. So the amount of CO2 is 0.608 mole. And we can also know the molecular weight of CO2, which is 44 grams per mole. And finally, we can calculate the mass of CO2 equals to this one. And the result is the same as this one. And so this is the first example. Another example I want to go through is about the concentration. So we have an example data reported from the laboratory, and the pesticide concentration in soil, and this is on a wet weight basis, and the concentration is 210 ppm or 210 microgram per gram. So this is better to be ppm. And then the wet weight of moisture aliquots is this mass, and the dry weight of the moisture aliquots is this mass. So the question is, what is the dry weight concentration of the pesticide? So to answer this question, the key principle is that the mass of pesticide does not change before for the wet weight and for the dry weight. So first, for wet condition, we know that the mass of pesticide is equals to the mass of the soil times the concentration of the pesticide. And we also know that for the dry condition, the mass of pesticide equals to the mass of the soil, which is only 39.5 times the concentration of pesticide. And because they are equal, so we have the equation as this one. And we can solve this equation. So the concentration of pesticide equals to and the result is 266 microgram per gram, or ppm, but it's better to have an m here. So this is a second calculation question. And then I would like to talk more about acid and base. I think you guys have already learned it before. So about pKa, it is an acid strength, and the pKa is defined as this equation. And in this equation, Ka is the equilibrium constant of acid dissociation. And for example, if we have acid like here, so this is a general expression of a strong acid, and it can dissociate AH+. And in this case, the equilibrium constant can be expressed as this, as we discussed in the lecture. And based on this definition, we can see that for strong acid, we will have very large Ka, because for strong acid, the concentration of acid will become 0. So that should be HAAB. The concentration will approach to 0, so the Ka will approaches to infinity. And we can also see that for a weak acid, we will have a Ka value, and which is smaller than strong acid. So the smaller pKa means stronger acid, because for the pKa we have the negative sign here. And then actually we can search for the Pka table to compare the acid. For example, let's just randomly find a Pka table like this one. We can see that this is HCl, the pKa is -8, which is very negative. And then like we have the some other acids like this one, and we can see the pKa is 5. So this acid, carboxyl acid, is weaker than hydrochloronic acid. And we can also see that water can also be considered as an acid, and the pKa is 14. So anyway, so we can use the Pka table to compare the strengths of the acid. And then let's look at an example about acid and base and pH calculation. So the question is, what is the pH of the nitric acid given this concentration? We know that the nitric acid is strong acid, so its dissociation is complete. So we can write the dissociation reaction or the chemical reaction of nitric acid. And we know that this is 1. This is also 1, because we are interested in the concentration of H+. And we know that the concentration of nitric acid is this value. And then we can calculate the concentration of H+ contributed by HNO3. And this ratio is straightforward. So we have this ratio equation 1 divided by the concentration of H+ contributed by HNO3, and we can solve this equation. So the concentration of H+ contributed by HNO3 equals to 2 times 10 to the -3 mole. And then the total concentration of H+ equals to the concentration of H plus contributed by the nitric acid plus the concentration of H plus contributed by water. And we know that for the water it is 10 to minus 7 mole. So we have this one plus this one, and compared with this one is very small. It can be considered as 0. So the total concentration of H plus is this one. And then we can calculate the pH, which equals to this one. And then the result is this one. So the pH of nitric acid of this concentration is 2.7. Then let's look at another example. So it asks, what is the concentration of OH minus in a HCl solution given this concentration? Again, HCl is strong acid. So the dissociation is complete, and we can write down the dissociation equation like this. And we know this is 1, this is also 1, and the concentration is 1.3, and this is the concentration of H plus contributed by HCl. And again, we can solve the equation, and we can get that the concentration of H plus contributed by HCl is 1.3 mole. And then the total concentration of HCl equals to the contribution from HCl plus the contribution from water, which is 1.3 plus 10 to minus 7, which is equals to 1.3, because this is too small. So, and we also know that the equilibrium constant of water is 10 to minus 14, which equals to the concentration of H plus times the concentration of OH minus. So we know that, so we can derive that we have 1.3 times the concentration of OH minus, and we can solve this equation, and then the concentration of OH minus equals to this one, and the result is 7.7 times 10 to minus 14 or 15 mole. So this is the result. And then let's look at another example, the last example. So the question is, what is the pH of HCl solution given this concentration? So I think we already have learned this. So I think you guys can try to practice, like press stop and do the calculation by yourself. Okay, so now I assume you have already do your calculation, and let's look at the result. So again, this is a strong acid, so it will become H plus and Cl minus, and this is 1, this is 1, this is 10 to minus 9, and we can also say that this is also 10 to minus 9, which equals to the H plus concentration contributed by HCl. And then the total concentration of H plus equals to the contribution from HCl plus the contribution from water. So this is 10 to minus 9 plus 10 to minus 7, which equals to 1.01 times 10 to minus 7 mole. And then we can calculate pH equals to log 10 and 1.01 times 10 to minus 7. So the result is 6.9956 7, 9, blah, 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 which almost equals to 7. So we can see that even though we add HCl, but the concentration is pretty low. It is only 10 to minus 9. So the influence is very small, and the pH of the solution will not change a lot. Of the water will not change a lot. It is still 7. So that's it.